Friction is also a reactive force, not proactive, which means if we were to actually have an object resting on the surface, it's not going to have any friction until some kind of push is basically applied to it. Okay? So force friction is only present if F push is present. So I use this example for my other class. Let's say we could calculate friction to be mu times F normal. And let's say the maximum value of friction that's calculated, right? So friction, F friction max, let's say is calculated to be 50 newtons, okay? Well, it could be calculated to your maximum amount of friction, but it doesn't mean it's 50 newtons right now and no other pushes are present. So here is my creamy butterscotch drops, right? It's Cavendish and Harvey. Now, right now, this box and this surface that is on, it has no friction. But we can calculate how much friction it can possess by using this equation right here. And let's just say, for easy sakes, that we calculate the maximum friction that this thing can possess happens to be 50 newtons. But right now it's zero friction because there's no push on this. Now when I apply 10 newtons of force, right there, there you go, 10 newtons of force right there, it's not moving. Since it's not accelerating, my net force is zero. If my net force is zero, the force push plus force friction opposing it have to add up to zero net force. Therefore, my force push is 10 newtons. My force friction has to oppose that. So my force friction now is only 10 newtons. Does that make sense? Now I'm going to actually apply with 20 newtons of force right there. Oh, there's 20 right there, right? Now my friction is only 20 newtons of force to oppose my push. So it's reacting to whatever push that I am giving this thing. Now let's say I push this thing with like 49.9999 newtons. Still not going to accelerate because my friction is maximum of 50. So the frictional force that's opposing my 49.99999 newtons is going to be exactly the same value as my force push, which is 49.99999 newtons. But what would happen if I apply 60 newtons of force? Louder? It'll accelerate, right? 60. Oh, there it is, right? Now, my net force is 60 plus negative 50 will be 10 newtons of force in that direction. So now it will accelerate because I have net force of 10, where friction now is only 50 because that's the maximum value you can calculate to. All right, so it's only going to react to whatever the push that exists, and then it could go up to 50 newtons in this case, and then it stays there. Okay, so that's very important concept for reactive force. Okay, now friction can be calculated with this funny looking U times the normal force. So what is this mu? Mu is a lowercase Greek letter m, mu. If you're from Kansas, you say mu, right? It's basically a pure number. It's a ratio of frictional force divided by the normal force, okay? And this mu value is different depending on what two surfaces that are rubbing against each other. So because of the imperfections on surface, right? For example, like vulcanized rubber on concrete surface, it would have a very high mu because they're both pretty rough. Wood and sandpaper, very rough, high mu. Okay. Wood and ice, very smooth, so small mu. I would always like to think of mu as level of pain. Higher the mu, higher the pain, right? I think we talked about like rubbing our face against like nice lathered up, you know, shower glass door. You're not going to feel any pain if you rub your face against that thing because it's very low mu. However, if you take that same face and put it on this concrete sidewalk and then rub it against the concrete sidewalk, you're going to scream. There'll be plenty of blood, high pain, very high mu. Okay? So if you think of it that way, it works out. There are two types of mu. Okay? There are two types. One being static, other being kinetic. Now, static coefficient of friction means not moving. Okay? So this is not moving. When things are not moving and there's a friction present, it's a static friction. For that, you have to use static coefficient of friction. For things that are moving, we use kinetic friction or the coefficient of kinetic friction. Okay? So when things are sliding and it's moving along the surface, you have to use coefficient of kinetic friction to calculate the kinetic friction. Usually, mu sub s is bigger than mu sub k. Okay? Why is that? Well, if you ever try to like move a box, large container, or large, you know, huge refrigerator or something, right? You push on it and it doesn't move. You push, right? You keep pushing, and then all of a sudden, when the thing starts to budge, it drops, and then you don't need as much force to keep it going. Okay? So, what's holding it back from sliding? All the push that I'm giving here is static friction, static friction, static friction, static friction. And then once it reaches the maximum static friction, then that static friction goes away. Now the kinetic friction takes over, and now the kinetic friction is what's resisting the slide. Okay? So the force that you apply, right, will drop, and then once it moves, inertia takes over. It wants to stay moving, so you don't need as much force to keep it going. And then this is mu sub k, and this is like mu sub s. Okay? And mu sub s and mu sub k are independent of the surface area in contact. So just because it's got wider surface area does not necessarily mean that it has more friction. Okay? Like say for example, here's like mass of 3 boxes stacked on top of each other, right? Your Fg is just 3 times mg, and your normal force is actually, right? Your normal force is 3 times mg. Okay? So if you calculate the friction, which is mu times F normal, this just becomes mu times 3 mg, which is 3 mu mg, right? Well, if I were to look at this, I have 3 masses along the side. Here I have mg, here I have mg, here I have mg. And the normal force, right, is mg for this one normal force is mg. Here, the normal force is mg. I have three frictions, right? Each friction is going to be mu times mg, right? Well, I have three of these joints, so I have to multiply that by 3. So my total frictional force is 3 times mu mg, which is exactly the same as this one. So the surface area doesn't really matter, okay? So the surface area doesn't matter. So are we okay with that concept? Okay. All right. Now the direction of friction will always be in the opposite direction of motion. Okay. There are some cases where the friction will act in the direction of motion, and that's very rare. And that happens when things are in non-inertial frame of reference or when friction is causing object to move. Okay. Because it wants to stay on top of things. But most of the times, the direction of friction is opposite of motion. So if you consider the direction of motion to be positive, your friction should most likely be negative most cases. Okay? All right. All right, so let's take a look at the next common force is the tension. Okay? Tension force, or force caused by strings, ropes, cables, etc. It is actually a pulling force. Okay, pulling force of string, ropes, and cables. You could only pull on the rope. You can really push on the rope. If you push on the rope, you're going to get hurt. Don't ever push on the rope. You can only pull it. Okay? Never push on a rope. So when that pull happens, this tension force will act always along the string or the rope or the cable. Okay? So don't get confused with the length of a rope as the magnitude of the tension. Just because rope is really long doesn't mean the tension has to be really big, right? Or just because you have a short rope doesn't mean the tension has to be small. The tension represents the magnitude of the pulling force that rope or cable or string possesses, not the length, okay? Tension force is a reactive force, just like friction. It's only going to react to how much pull that the rope experiences. Okay, so if the rope experiences greater pull, the tension is going to be that much greater. Okay, so something must pull on the rope to have tension in the rope. Because if there's no pull, there's no tension. Okay, so here's a one good example to have. Okay, make the direction of motion to be positive. Make the direction of motion or its intended motion, okay? So it may not be moving, but it's intended to move in that direction. So if that's true, then since friction will oppose the direction of motion or resist from sliding, then friction will be in the negative direction most cases. Okay? Now, in convention wise, since I am pulling this thing along this direction, it probably will not be going along that tension direction. If this tension y is greater than my FG, then yes, this thing will be lifted off this surface and it'll be accelerating along that direction. But if this tension y is less than my FG, it's going to stay on the ground and it's going to move along the ground parallel to the ground. Okay? So you really have to calculate if this is going to be bigger than this or not, usually, to figure out if it's going to stay on the ground or not. If Ty is bigger than Fg, then this is going to be lifted off. I'm going to consider the direction of motion to be positive. Therefore, looks like it's going to be moving this way. So I'm going to consider this direction to be positive direction and the opposite of that to be my negative direction. And I will also consider the direction up to be positive in this case and direction down to be negative. Okay. So we should be able to identify, right, all the forces acting on this object. Okay. Once we understand all the forces acting on the object, we could draw the force diagram, and we call that free body diagram. And free body diagram is same as force diagram. Okay. That is drawing all force vectors. Okay. Okay. Acting on the object. Okay. Then break up all force vectors into x and y components. Okay. So if we were to take a look at all the forces involved, and then there are three forces here. We have Fg, which is caused by gravity. We have F normal, which is caused by the surface to the object. And we have tension, which is force being pulled by a rope. Okay, so we have three forces. If I break these up into components, this looks like it's in the y direction, this looks like it's in the y direction, but this one looks like it's in the x and y direction. So this is the only one we need to break up, really, right? So if this were to be the angle theta that this thing is being pulled, my ty, right, is really the opposite of my angle theta, so that is t times sine of theta, right? And my tx looks like t times cosine of theta. Okay? So let's take a look at the y direction first. Okay? If we look at the y direction, how many forces are there in the y direction? Looks like one, two, three forces, right? So there are three forces in y-axis, right? Or y direction. I always start out with my Newton's second law. So sum of all forces is equal to ma. That's Newton's second law. But since I'm looking at y direction, sum of all forces in y is equal to ma y. Now notice how these are vectors, right? The net force in y, a in y are vectors. So this is what I always start with. Always start with this equation. Then the second definition of my net force is just adding up all the forces. But since I'm only looking for the net force in y, I'm going to add up all the forces in y direction only. So it looks like, F normal looks like it's going in the y direction. Right? This is Fg, which is force of gravity or weight. So plus Fg plus Ty. So this is the definition of my net force, adding up all the forces. But since I'm net force in y, all the forces in y directions. So these two are crucial. But this is easy. You just have to remember the F equals ma. But identifying all the forces in y direction is very important. Now, since this is exactly the same as this, I can set these equal to each other. So m a y is equal to Fn plus Fg plus Ty. Now give direction, right? Now give direction to all forces. So here, we don't know which direction AY is, but we pretty much know that it's going to be zero because it's not going to be like levitating off the surface or it's not going to go through the surface. So you know my AY is going to be zero. But if we don't know that, we could just leave it as MAY. And hopefully these will algebraically give me the proper directions for my acceleration later on. But for now, just want to leave it as MAY. I definitely know my F normal is pointing up, so I'm going to call that positive direction. So F normal is positive. My FG, however, is pointing downwards, so I'm going to call that negative direction. So my FG is negative FG. My TY is pointing upwards, so it's positive direction. So my TY is positive, so plus TY. And if I consider my acceleration in the y direction to be zero, my zero is equal to then F normal minus mg plus t sine theta. Now my F normal, if I were to solve for it then, my F normal then is equal to mg minus t sine theta. This doesn't mean this is not something that you memorize. This is just happens to be what we derive for just this problem. Because other problems can have like multiple tensions, right? So multiple applied forces. So this just happens to be what we derive for this particular problem only. So don't try to memorize this and use it because it's not going to be same for all problems. Okay. Now let's take a look at the x direction. Question. Fg is equal to mg. So I substituted the Fg with mass times acceleration due to gravity. Does that make sense? So Fg is just m times g, and Ty is t sine theta. Ben, you have a question?
Yeah, why are we assuming acceleration is zero? Because isn't there like gravity, like the y direction at least?
Well, yes, that is true. However, is this object going to be levitating off this surface?
Like because the force pushing back up on it
Right.
means okay.
Is this thing going to go through the? Is this thing going to go through the ground? We don't know. It's not going to happen usually. So the acceleration of this in the y direction is going to be zero by itself. Does that make sense? Okay.
Yeah.
All right. Now let's take a look at the x direction. If we were to look at the x direction, right? There's only one force. Right? There's only one force. And that is just the tx in the x direction. Okay? So here, again, I start out with sum of all forces, or the net force in the x direction is equal to max, Newton's second law. Okay? And then I add up all the forces in the x direction. In this case, we only have one, and that is just tx. Okay, so again, this is important. Now, identifying what the net force is important. So we can say now max is equal to just tx. Now let's give direction. Okay, give direction to forces. So here, max, which we don't know which direction is going to go. Most likely it's going to be positive though, because whatever this tx is, that's my x direction. Tx is definitely positive direction, so we're going to say tx, and that's it. So my acceleration, max, is equal to t cosine theta, and my ax is equal to t cosine theta over m. Is that good? Okay. All right. Well, let's extend on this. What if there were friction? Which way would the friction go? Which way would friction point? John? To the left. So friction would point to the left this way, and that direction looks like it's negative direction. Okay? So this is with friction now. This is with friction. This is without friction, all this right here. But this is with friction. With friction, friction only acts along the x direction, so we're not going to worry about the y direction because y direction is going to stay the same. But it's only going to affect the x direction. Okay? So with friction, we have sum of all forces in the x direction is equal to max again. Right? Again, this is Newton's second law. This time we have two forces in the x direction. Sum of all forces in the x is equal to, I have tx plus friction. I have two vectors, two force vectors. I have to add those two vectors, right? So here, MAX is equal to TX plus friction. Now I'm going to take the vector symbols out by giving direction. Now give direction to forces. Okay? Now, if I give directions to the force vectors, my MAX, which we don't know if it's going to be negative or positive, so we can't really give direction to this yet unless we know. Here, TX is T cosine theta, right? Minus friction, right? Minus friction. So my MAX is equal to T cosine theta minus mu times F normal. We know what F normal is. F normal here is this culprit right here. So we can say MAX is equal to T cosine theta minus mu times mg minus T sine theta. Running out of room. So my acceleration in the x is equal to T cosine theta, right, minus mu mg plus mu T sine theta, whole thing over m. Again, don't try to memorize this. You should be able to derive this equation depending on what's given to you in the problem. These all have to be derived. Don't try to memorize it. You cannot memorize and use it on different problems. Okay? Yeah. Well, friction by definition is mu times F normal. Yeah. Because we already calculated the F normal on this side from the y direction. Does that make sense? Did you guys hear that question in the cyber world? She asked, where did you get this F normal? How'd you go from here to here? Well, mu times F normal is friction, right? And this F normal was already calculated from the y direction, which is mg minus T sine theta. So that was substituted in here. All right. Good. Any other questions? Okay. Now let's see if we can take a look at the next one. Now this one, you have to think about it. We have a 10 kilogram, object 3 CT. Talk about typo. We have a 10 kilogram object is subject to the two forces, F1 and F2, as shown below. Think about this is like out in space, far away from gravitational influence, right? It's just floating out in space. And we're looking at this from the bird's eye view, where two forces are acting on this simultaneously on a plane, right? Even though it's out in space, it's like we're looking at a plane because we're looking straight down at it, okay? So if I were to pull on this 10 kilogram object with two forces acting simultaneously like this, right? It's going to behave as though only one force is acting that way, and it's going to behave as though it's going to be pulled in that direction where the net force is going to go. Does that make sense? Okay? So by pulling on this simultaneously, it's going to behave as only one force, which is the net force, is pulling on this by itself. Okay? So they want to know what is the acceleration of the object, and if the object starts at rest at t is equal to 0, how fast is it moving after 3 seconds? And find the third force, F3, that's needed to stabilize this equilibrium. This we did probably in chapter 3. However, to do this, I think the best thing to do is to find all these forces in the Cartesian form. I think that's the easiest way to do first. So find the forces in Cartesian form. So if you were to think about F1, here's my F1. So F1 can be represented as, looks like it's only going in the y direction, right? So it looks like 0 x hat plus 20 y hat newtons. Okay, and then your F2, looks like this is F2x, right? So this is F2x, and then this is F2y. The angle 30 degrees here is actually a negative angle, right? So the proper angle is 330 degrees. So since F2x is F2 times cosine of, right, theta, F2x is 30 times cosine of 330 degrees, or negative 30 degrees. If you do that, I think you get something like F2x is equal to 26 newtons in the x hat direction. So here I get 26 x hat, and F2y, right? F2y is simply F2 sine of theta, and F2y is equal to 30 times sine of 330, and that comes out to negative 15 newtons y hat. So plus or minus 15 y hat, okay, newtons. Well, since sum of all forces, my net force, is equal to, right, simply F1 plus F2, I can say, all right, well, let's add these forces up. So my F1, therefore, F1 is equal to 0 x hat plus 20 y hat, and F2 is equal to 26 x hat minus 15 y hat. So when I add these two forces up, I get my net force. And that is 26 x hat plus 5 y hat newtons. All right. So this is my net force in Cartesian form. So that looks like it's going to be going somewhere, like here. In this direction. So that looks like my net force, which is like 26 positive 5. Okay? And I bet we can find the magnitude of that net force. And that is basically square root of 26 squared plus 5 squared. And that comes out to something like 26.5 newtons. And theta is equal to this theta right here, tan inverse of 5 over 26. And that comes out to something like 10.9 degrees. All right, so now we can start this problem. Now, you don't have to go through all this to start it, but it's also nice to figure this thing out so that now if you were to look for part A, what is, part A asks, what is the acceleration of the object? Well, for part A, acceleration, according to Newton's second law, is directly proportional to the net force and inversely proportional to its mass, right? So by this straight definition, my acceleration can be calculated as my net force, which is 26 x hat plus 5 y hat. And if I divide that by mass, which is 10 kilograms, right, my acceleration is really nothing more than 2.6 x hat plus 0.5 y hat meters per second squared. Okay? That's the Cartesian form of my acceleration. Or you can simply say, well, my acceleration magnitude is the magnitude of my net force divided by its mass, and that is 26.5 divided by 10. Right, this is newtons, this is kilograms, and this should come out to 26.5, 2.65 meters per second squared. 2.65 meters per second. Now that is exactly same as this squared plus that squared, square rooted, should be the exact same thing. All right? So the acceleration is 2.65 meters per second squared. But what about the direction? Well, the direction theta is exact same theta as the net force theta, which is 10.9 degrees. So you can also represent that as, right, 2.65 meters per second squared, comma, theta is equal to 10.9 degrees. They're exact same things. So if they want it in polar form, you do it this. If they want a Cartesian form, you give them that. All right? All right, what about part B? Part B says, if the object is at rest at t is equal to 0, so initial velocity is 0, how fast is it moving? So they want to know how fast is moving Vf when t is equal to 3 seconds. We know the acceleration. We just calculated the acceleration to be 2.65 meters per second squared. Well, this looks like equation number 1, which is Vf is equal to Vi plus At. So Vf is equal to Vi, 0, plus 2.65 times t of 3 seconds. So final speed of this is equal to 7.95 meters per second. Now, if they were to ask you, what's the velocity of this thing, right? Then it is just 7.95 meters per second, 10.9 degrees. But if they're asking for what's the speed of it, it's just 7.95 meters per second. All right. Now for part C, they're asking, find the third force, F3, needed so that the object is in static equilibrium? Well, if we know the net force, right, the net force is going this way at 10.9 degrees at 26.5 newtons, right? Well, the net force opposite of that will stabilize that, right? So this can be F3, the opposite direction, right? So since F3 is equal to negative, right, net force, yeah, yeah. Oh, you have a question?
Oh, no, I figured it out.
Sorry.
Thank you.
I just get so involved in my own world. Thank you. Once in a while, you have to shout it out. Yeah, sorry. So since it's negative, right, net force, my F3 then is equal to negative of 26x hat plus 5y hat newtons. So what's my F3? My F3 then is equal to, right, negative 26x hat minus 5y hat newtons. Or you could say F3 is equal to 26.5 newtons, where theta is 180 plus this theta right here, which is opposite direction. So 190.9 degrees. Voila. Any questions? All right. Okay, moving on. Here looks like a normal force problem. Here's an example of a 10 kilogram box of chocolates. Ooh, 10 kilograms. That's like 23 pounds of chocolate. That's a lot of chocolate, right? Life is like a box of chocolate, right? You never know what you're going to get inside until you bite into it. And once you bite into it, you don't like what's inside, just put it back in the box and let somebody else eat it. Yeah, that's life. That's what life is all about, right? It's all about me, and me. So a 10 kilogram box of chocolate is resting on a smooth, frictionless horizontal surface of a table. Okay. A, determine the weight of the box and the normal force acting on I dot. That should be it. Wow. Okay. So for part A, if you were to think about a box of chocolate, I'm just going to draw the whole three in there. There's going to be three scenarios. So I'm going to draw a box of chocolate right here for part A. Okay, so this is part A. We have a 10 kilogram box of chocolate. Well, this 10 kilogram box of chocolate will definitely have influence by gravity, and it will have Fg going straight down, and that is equal to mg. Your Fg is equal to mass, which is 10 kilograms, times acceleration due to gravity is 9.8. Therefore, your Fg is equal to 98 newtons on Earth, no matter what. Okay? Well, this weight has to be supported by the surface of this table. So this table will support this 10 kilogram chocolate by producing the normal force up from the surface to the box of chocolates. We don't know how much that is. So we're going to say, okay, well, the net force in y direction, again, is equal to MAY. Again, we start with this equation of Newton's second law. And since we're only looking at the y direction, it's Fy is equal to MA1. Well, how many forces are there in the y direction? There are two forces. I have F normal and I have Fg. Therefore, if I set these two equations equal to each other, my MAY, right, is equal to F normal is definitely positive because it's pointing upwards. Okay? Or do you want me to take one more step and just say, okay, I'll take one more step instead of skipping it so you guys don't get confused. Is that good? Now give direction, right? Now we're going to give direction. So MAY is equal to F normal positive, Fg negative. But is this box of chocolate accelerating through the floor, or is it levitating off the floor at all? No. So my acceleration in y direction for this chocolate is 0. So my F normal minus Fg is equal to 0. Now this Fg is already, we know it as 98 newtons. So my F normal is equal to simply 98 newtons. So in this particular case, when there's no other vertical forces acting on it, only the gravity works on it, then my normal force is exact same value as my weight of this. But what about a second scenario where I have a box of chocolate again, right? This 10 kilogram box of chocolate. Now, this will have, again, the same Fg, straight down. So this weight of this box of chocolate will not change because Earth gravitational pull will not change. The mass doesn't change. So it's still going to be 10 times 9.8 or just 98 newtons for my Fg. Okay? However, I have 40 newtons of force acting down. It's pushing down on it. So I have 40 newtons of force, right? So I have F push is equal to 40 newtons in downward direction. So my normal force is going to have to basically support both of those forces, okay? course, this is not accurate drawing right here, but we got to find what that normal force is. So again, I will start with Newton's second law. Right? Sum of all forces in the y direction is equal to ma y direction. And sum of all forces in the y direction is equal to, right? I have three forces now. F normal force plus weight, Fg force, plus my force push. So I have three forces. Now I have to set them equal to each other. So set these two equal to each other. Okay. Then my MA, right, in y direction is equal to, right, F normal plus, right, Fg plus F push. I know this is very easy, but I'm writing it all out because this is the way you should always solve it. I know some of you already have the answer in your head and did it in your head, but I want you to follow this methodology so that it never goes wrong. So MAY, I'm going to give directions now, is equal to F normal. Looks like it's positive direction because it's pointing up. Okay, so I'm going to call up positive, down negative. Okay, so here my Fg is negative Fg, and force push is also negative F push. Again, my acceleration in the y direction is 0, so this whole term goes to 0. Now I have F normal, 0 is equal to F normal, minus 98, minus 40 is equal to 0. So my F normal now is equal to 138 newtons. If you don't know how I got that from here to here, come talk to me after school. We have a nice long heart-to-heart talk. All right. Now for part C. So this is part B. Right? And for part C, same scenario where we have a box of chocolate here. Right? Now we have Fg again going straight down towards the center of the earth. So here's my Fg, which is equal to mass times acceleration due to gravity, which is 10 times 9.8, and that is 98 newtons. Still, that's my Fg. That's the weight of the box of chocolate. Now, instead of pushing down on this thing, I'm pulling it up. So my F pull, I should say, is going to be 40 newtons in the upward direction. Right? Now it's being pulled up with force of 40 newtons. So now my F normal probably don't have to support as much. Because it doesn't need it. Okay, so that's my prediction. So let's figure out what the value is. Again, I start out with my net force in y is equal to MAY. My net force in y is equal to, I have three forces acting on this, right? So I have F normal plus Fg plus F pull. Okay, since these are all vectors, okay, you're just adding up all the vectors. So my MAY is equal to F normal plus, right, plus FG plus F pull, okay? So MAY, I'm giving directions now, is equal to F normal minus FG plus F pull. This is important from this step to this step, because you have to really make sure you give the right directions to this. Okay? And my AY is 0. Therefore, my F normal minus 98 plus 40 is equal to 0. All right? So now you can see that F normal now is equal to just 58 newtons. It doesn't have to support as much as the weight of the object. All right, so let's see if I can move this up like that. All right, Sharia, you have a question?
Yes, more clarification, but like for F and G, why isn't it negative 9.8 instead of?
It is. That's why I gave direction here.
Oh, okay.
This makes it negative. Now, if I do put that negative 9.8 by giving a direction already, I cannot put direction in here anymore. So you have to do either one.
Oh, okay.
Okay, so you don't want to give direction twice. So it's, yes, if you want to use negative 9.8, you just have to just put it as whatever the value that is and use it as plus here. Okay? Good question. So if you're going to do it that way, then you better make this negative 40, right? So if you want to give directions in the beginning, then you just basically add all the directions up here straight out that you already gave directions. Good. All right. Any other questions? All righty. All righty. We're moving right along. Okay. Let's take a look at this bucket problem. Okay. 10:52, 12 minutes. Okay, that should be fine. All right. So we have one paint bucket weighing 40 newtons is hanging from a massless cord. I love these massless cords. For Christmas, if somebody can give me massless cord, I'd be so happy. From another bucket weighing 40 newtons. I'm going to change this around and I'm going to make this one 60 newtons instead of 40 newtons. So this is going to be 60 newtons and this one's going to be 40 newtons. Now this is weight of the bucket, not mass. Okay? So this is actually FG bottom bucket, and this is FG top bucket. Okay? So if you were to think about this, right, the mass of the top bucket is equal to basically FG top over G, which is 60 divided by 9.8. So the mass of the top bucket is equal to 6.12 kilograms. And similarly, the mass of the bottom bucket is equal to FG bottom, divide that by G, and that is equal to 40 newtons divided by 9.8 meters per second squared. The mass of the bottom bucket comes out to 4.08 kilograms. Yeah, that word bottom sounds very naughty. All right. The whole system is accelerating at 1.5 meters per second squared. And since it's accelerating upwards, I'm going to consider the direction up to be positive, right? Positive, right? And down is going to be negative, okay? So to do this, I would start out from, there's so many correct ways again to solve this, right? There are invisible tensions here, right? That you cannot see, but obviously the tension of this is going to be much greater than tension of this. Does that make sense? Right? Let's say this is not accelerating. Like there's no acceleration. Let's say it's just hanging around, just hanging on the top of the ceiling. What would this tension be here? Umar? 100 newtons, yeah. If it's not moving, it's just going to be 100 newtons. So you've got 40 newtons, 60 newtons. This better be 100 newtons. What about this tension here? 40 newtons. So that's easy, right? But what if this thing is accelerating this way? You think this tension is going to be more than 100 or less than 100? Definitely more, right? Definitely more. So that's a good thing to know in our head before we even start the problem. And obviously this has to be more than 40 newtons, right? So let's take a look at this. I draw a free body diagram again. This is very important, right? Free body diagram. A free body diagram means isolating each mass or each object from the system and draw the force vectors on it. Okay? So here, I will actually draw this one down here where I have, here's my bottom bucket. And let's draw all the forces acting on that bottom bucket. How many forces are acting on that bottom bucket? Come on, how many forces? 2. Very good. Which are they? What's the obvious one? Gravity. Fg bottom. Good. And tension. Yeah. The tension. I'm going to say tension bottom because it's the bottom bucket. Okay, tension bottom. Now, since this thing is accelerating up, I'm going to call that up positive and down negative. Okay? So we know the Fg bottom is already 40 newtons. The acceleration of this bucket is same as the acceleration of the whole system, which is 1.5 meters per second squared. So sum of all forces, right? Sum of all forces for the bottom bucket is equal to m bottom times A. Now A is common for a whole system. And we said there were 2 forces for the bottom bucket, and that is Fg bottom, right, plus the tension bottom. So MBA, MBA is equal to, right, Fg bottom. Is that positive or negative? Negative. Negative Fg bottom. Tension bottom is positive in this case, right? We know the acceleration is positive 1.5. We know this is 40. The mass we already calculated. So we could calculate for the tension bottom. So the tension bottom is equal to Fg bottom plus MBA. So tension bottom is equal to 40 plus 4.08 times 1.5. So the tension bottom comes out to 46.12 newtons. Booyah. All right. Now let's take a look at the top bucket. This top bucket here, if I were to isolate this top bucket and draw a free body diagram on it, right? Here's a top bucket. How many forces are acting on the top bucket? How many? 3. Very good. Which are they? What's the obvious one? Gravity. Fg top, which is 60 newtons. Good. What else? Okay, so tension bottom, right? Tension bottom. We already calculated that to be 46.12 newtons. Good. And then tension A or tension top, right? Those 3 forces are, somebody's going to ask me like, but Mr. Kim, what about the weight of the bottom bucket? Are you just throwing that out? And I'm saying no, because the weight of the bottom bucket is already built into this tension bottom. Okay? So now I can say sum of all forces for the top is equal to m top A, right? And sum of all forces for the top is equal to 3 forces, tension top plus Fg top plus tension bottom. Okay? Therefore, MTA is equal to tension top positive, obviously, minus Fg top bucket minus tension bottom. So if I solve for tension top, my tension top is equal to, right, MTA plus Fg top plus tension bottom. So my tension top is equal to, right, 6.12 times 1.5 plus 60 plus 46.12. So my tension top is equal to 115.3 newtons. All right. Wow, perfect timing. Work on your homework packets. Even though if I don't assign it, you should be continuously working on that to a point where you should be almost halfway done. So work on your homework packet. I guess I won't see you until, is it Monday? Well, not you guys, I guess, but for you guys, it's Friday. Oh my God. All right. Well, have a wonderful weekend for you guys. And then for virtual world, I'll see you guys on Monday. All right. Ciao.